This case where the fields don't vary with time, in other words, dB by dt is naught, the magnetic field is static, and dE by dt is naught, well, then the equations seem to split into two completely different groups. And indeed, this is precisely how electrical effects were first investigated. They were at first thought to have absolutely nothing whatsoever to do with magnetism. And we'll come to how it all goes together in the next few weeks. But today we're just going to look at this. Now I'm going to review this very briefly. In the notes that I put up on the VLE, I've done some, if you like, essential revision from the physics and fields and waves from Kieran's course. There's like chapter 21 on electric charge and field, chapter 22 on Gauss's law, chapter 23 on electric potential. And looking at Kieran's lecture notes, I mean, he took 7 lectures to cover this material. And I'm going to review it very briefly, but mainly what I'm interested in is putting together how this equation is the same as what you've learned previously. So again, the blackboards in here aren't great. You know, as you see, I've only got one board on this side, one board on this side. So today I might use some scribbling on view graphs for notes. And indeed, the most important, and in fact, more or less essentially the only board notes that we really need is this idea. So to make sure everyone's kind of got time to put this up, I'll write it myself as well. This is that Maxwell's first equation. So this is del dot E, the divergence of the electric field at any point is equal to the charge density rho at that point divided by the permittivity of free space. And because, you know, we're starting, all right, I know we've given this a number before, but it's more convenient to relabel it 2-1 in this lecture as we put things together. And then we've got Gauss's flux law of electrostatics. This is what you studied for, as I say, at least 7 lectures, and then when you went on to study capacitance, effectively you're also studying this. So half of Kieran's course, more or less 9 of the 18 lectures, were on electrostatics. And this law is the surface integral of the normal component of the electric field integrated over the surface is equal to the volume integral of the charge density divided by epsilon naught times, integrated over the volume inside this surface S. And I'll make that equation 2-2. And then if we go right back to the normal sort of way we start off studying electrostatics is via Coulomb's law, in which the force between two charges Q1 and Q2 is equal to the product of the charges divided by 4 pi epsilon naught r squared times a unit vector in the radial direction. This is a unit vector that points along the line between charges Q1 and Q2. And this is equal to, if you like, to Q1 times the electric field. Let's make that equation 2-3. And where the electric field is this, and we assume that charge 2 creates a field E, and then when we put charge Q1 into that field, it experiences this force. And again, I should say it was a tricky decision for me that I think that, unfortunately, this is an E with a subscript R and a hat. This is a unit vector in radial direction. Now, the reason that I chose this is partly because it's the same as used in the Feynman lectures that I've recommended. But I'm uncomfortably aware that my symbol for an E, when I'm handwriting it, is a little bit similar, or very similar, to Greek rho. But, you know, be careful as you go along. Certainly, we'll never have a rho with a hat on it, rho's a scalar, it certainly can't be a unit vector, and it won't have a subscript r. So please don't confuse those. Now, I'd like to make a comment about a different nomenclature with Kieran's course. He wrote this side. Again, I've run out of Blackboard space already. I love this lecture theatre. Oh, God. You all know what Maxwell's first equation is by now, and it's that was in the lecture yesterday. So I'd like to now just compare this with what Kieran used, and that is, he wrote that this is the surface integral of E dot, and then, he actually used, this is a trivial difference. Everyone's got their own style. Kieran used a sort of a tilde type underscore for fields. But then ds here, and he wrote this is equal to Q enclosed over epsilon naught. Now, there are one or two features that I'd really like to bring out with the differences here. First of all, and I mentioned this when we did Maths 1, a long time ago, but I hope you can remember that basically, of course, I'll just grab a little teaching aid here. A box, in fact. There's lots of demonstrations today. Here we've got a box. And basically, of course, this surface, imagine it's infinitesimal, but you wouldn't see it, so I've used a slightly larger than an infinitesimal box. This surface clearly doesn't have a direction. It's the normal to the surface that has a direction. And so this symbol, in a way, is a compaction of two ideas. That what Kieran was saying was that this is ds. I prefer to think of the area of this infinitesimal surface element as a scalar, and then I have a unit vector pointing perpendicular to it. And in some of the derivations I do, it's not just that I want to have the same nomenclature as Feynman. Feynman uses it in exactly the way I've written equation 2 here, but I want to emphasize that there's two ideas contained in this. One is the surface normal, and one is, if you like, the magnitude of the area element. And then on the right-hand side of the equation, Kieran wrote this as the charge enclosed by the surface S divided by epsilon naught. Well, of course, the charge enclosed is obtained by integrating the charge density over the volume. If I've got some arbitrary volume, and inside it I know the charge density at every point, and I integrate over the volume, remember this one's in coulombs per cubic metre, and I integrate over the volume, of course I get the total charge enclosed. However, this is now, if we want to link up our new way of looking at electrostatics with the previous way, it's important to write this as a volume integral rather than just the total charge enclosed. So you've done this before, and also one of the things you've done before, but which I'd like to review, is that Coulomb's law and the Gauss flux law of electrostatics all express the same physics. There's nothing different in terms of the physical content of equations 2.1, 2.2 and 2.3. They all look very different. Now again, Kieran did this derivation, but I shall just very briefly run through it again, provided one of the things that's not changed from last year is the view graph shuffling monster has already been at work. But let's have a look at why Coulomb's law is the same as Gauss's flux law. Well, the idea of let's put a point charge at the origin and surround it with a sphere. So let's imagine that we have got a point charge at the centre of this tennis ball. This is an imaginary surface, but a tennis ball is easier to see than an imaginary surface. So clearly we are using actually ideas like underlying ideas like isotropy of space, we're assuming that there is absolutely no reason why the electric field should be different here, or here, or here, or here. We're assuming that space is isotropic, so the charge produces an electric field which spreads out radially. So clearly, if we now apply this law, the electric field is radial, so the surface integral, we can write now E dot n is clearly just equal to the magnitude of E. Because if we're assuming that the field, let's have the field as a biro and the local unit normal as a view graph pen, it is always just pointing radially outwards. Well, clearly in this simple spherical geometry, the normal vector is pointing radially outwards. So at any point, they're always parallel. The normal vector and the electric field are parallel. They're parallel here, they're parallel there. And this is why I like to split these two concepts into the dot NDA. You'll see this is a two-stage type calculation. So I can say, well, E dot n is therefore just equal to the magnitude of E. You know we've done scalar products of two vectors, and we know that we've got the E dot n is the magnitude of E times the magnitude of n times the cosine of the angle between them. They're always parallel, so the cosine is equal to 1. The magnitude of a unit vector is obviously equal to 1, so I can replace the E dot n with the magnitude of the electric field at any point. But now I'm also assuming there's no reason for the electric field to have a different magnitude at any point either. Why should there be more electric field going up through the North Pole or the equator or any other arbitrary direction? So, of course, this is constant at any given fixed distance r. So I've just, and again, I've mentioned this in the course last year, rather than write the magnitude of the vector E, I might just write E for its magnitude at that point. So when I do this integral, the electric field is also constant at any point on the surface. Its magnitude is constant. Therefore, it comes outside the integral. It's a constant. So my surface integral is just the area of a surface. Well, we all know that if I integrate, if I get the area of a surface, we just know it as a formula. It's 4 pi r squared. So clearly, the left-hand side of Gauss's flux law of electrostatics is E times 4 pi r squared. In this case, this thing here becomes E times 4 pi r squared, and we've now got, clearly, if we've got a point charge at the origin, we don't need to even bother with doing an integral. We've just got a point charge at the origin, which is enclosed by the sphere, and therefore the right-hand side is just Q over epsilon naught. So this gives us the electric field, and this gives us the well-known inverse square law. And then if I multiply this, so this is exactly, gives me, we've written into our calculation that the field is radial, so we've already got this unit vector here. This is the magnitude of the field, and then we put a test charge in the field, and it experiences this force. So you've already seen that Coulomb's law and Gauss's flux law of electrostatics are the same thing. Now, before we go on to, let me just, I think, again, I'll make one or two tiny board notes, because you've done this last year. Actually, this will get hidden, so I'll have to clean the blackboard, having made one line. Coulomb's law is an elementary way of learning electrostatics, and let's just say it is straightforward. Yeah, we just did it. It's not rocket science, this bit. It is straightforward to prove that equations 2,2 and 2,3 describe the same physics, as I claimed at the beginning. So we've already seen that we can go over from Coulomb's law to Gauss's flux law of electrostatics. I'd just like to mention that this is slightly off the wall, but I think you might find useful in your kind of like general studies. Of course, the same thing applies to Newtonian gravitation. It's an identical argument, and this is indeed why Newtonian gravitation is an inverse square law, but in this case we just replace charge with mass and it creates a gravitational field. But it's a point mass at the origin. We then surround it with a sphere 4 pi r squared, and the field lines spread out over the surface of the sphere, so gravitation is also an inverse square law, has to be. This is just, if you like, a consequence of the idea of flux coming out from some point. Charge creates an electric field, mass creates a gravitational field. In a gravitational field, we then pop in. We just have, of course, the constants are different. You have 1 over 4 pi epsilon naught, or Newton's universal constant of gravitation, but it's clearly, by the same argument, got to be an inverse square field. Now, one of the things that people sometimes find difficult with the concept of flux is that for electric and gravitational fields, nothing's flowing anywhere. The charge just creates an electric field. The electric field isn't some flow of anything. Flux is an old word for flow, but we keep the word flux. It's perhaps easier to think of it, if you like these kind of analogies. This is, again, must be an inverse square law. Let's say we've got a little point heater. Might be some bit of radioactive material, tiny piece at the origin, and it's producing so many watts or joules per second. And then the heat flow, if we've got an isotropic, of course, we're not talking now about convection and directional things, but let's pretend we've got an enormous block of material and there's only conduction. So that flows out the heat from this source. Let's say it's hot there at the source, it's cold out here. Heat will flow from the centre outwards. But then the heat flow, we go through the same argument. The heat flow vector is radial, so we only need to consider its magnitude. Because we're inside this big block of conducting material, then likewise its magnitude is the same at every point. So by conservation of energy, W has got to be equal to h times 4 pi r squared. H is now the flow of energy per second per square metre. It's got so that our local vector here, let's say this is a little bit of the surface, there's my heat flow vector. Well, of course, the heat flow is going to be in joules per square metre per second. I integrate that over the surface and I get the number of joules per second passing through the whole surface. And this, again, will be an inverse square law. And in a sense, this is easier now to understand flux, because we can actually think of heat flowing through this surface. In this case, the vector field really does represent flow. So sometimes, if you find conceptual difficulties, it's worth considering this analogy with heat flow. So that was a slight aside, if you like, on gravitation and heat flow, but it's to emphasise that the inverse square laws are perfectly general for having a point at the origin and a field that just spreads out radially from that point. So the new physics to you is that I now want to prove that equations 2.1 and 2.2 describe the same physics. So equations, is that visible over this? Yeah. Equations 2.1 and 2.2 are related by Gauss's theorem. And again, it's a bit unfortunate. Gauss, of course, was an extremely clever man, and he was a brilliant mathematician and also investigated electricity. Gauss's theorem in pure mathematics is, as I'm sure you all know off by heart, let's clean this board up, that the surface integral of a vector field is equal to the volume integral of the divergence. So Gauss's theorem, and this is pure maths, so I'm going to write this again in the spirit of what I introduced as the vector field C, which is because it's just generally true. So the surface integral of the normal component of any vector field is equal to the volume integral of the divergence of the same field. Now, there is absolutely no physics in that at all. That's true by virtue of C being a vector field. Now again, I mentioned that it's good to, of course it's great if you're good at maths and you understand everything that, you know, from your maths course last term and you're totally happy with Gauss's theorem and Stokes' theorem. But we're going to be using these again and again. So for the next few minutes, I'm going to do, if you like, an intuitive sort of proof of Gauss's theorem to make sure everyone's got a feel of what this is telling us. And now, this one is excuse me, I've got a potato here actually, and a knife. Oh no, mad axe-wielding lecturer in physics, you know, no. Don't worry, you're quite safe. I'm only going to use the knife on the potato. And not, hopefully you've all got a handout. The view graph shuffling monster took my view graph of this. If you look over to, there's some oddly numbered view graphs at the beginning which go -6, -5, -4, -3, -2, -1, 0. Now, I'd already prepared the whole course view graphs, if you like, just for the electromagnetism. And I was going to say, oh, you've all already studied, you know, maths 2, so I don't need to go over that. But as I say, one of the things where people sometimes struggle with this course is putting the maths and the physics together. So I'm not going to go through the whole of this. On the VLE, there is a complete derivation in the Feynman style, which I'm copying, of Gauss's theorem and also of Stokes' theorem. And if you feel remotely shaky, please do go to the VLE and look at those and or read it up in the Feynman lectures. And now the crucial part is, I would say, the two crucial parts are figures -1 and 0 at the bottom. There's a lot of stuff in general about vector fields on this VLE description, but there's also a derivation of Gauss's theorem, which I'm going to just briefly go through. And you can see, by a certain accident, figure -1 does actually look a bit like a potato. And the idea that's being illustrated in figure -1 is that we make a cut across the centre of the potato. So let's do it. There we go. That's my Nigel Slater impersonation. Just knock up a little stew while I'm giving a lecture. There we go. I'm going to cut it. Now, the point is that the flux across this surface must be exactly equal and opposite to the flux across this surface. I'm not saying by any means that the heat has got to be flowing across the surface. It can be flowing at any arbitrary angle, as illustrated in the figure. You'll see that there, the vector field C, it's done in general. You can think of heat if it's, you know, a baked potato or something. But the illustration, so there's the kind of potato-y shape, can be any arbitrary shape. I'll cut it across here, and at some point the heat flow vector might be like this. But the surface normal to this side is equal and opposite to the surface normal to this side. So when I take h dot n on this side and h dot n on this side, they cancel each other out. So at any point, all of the flux coming out of this surface is equal and opposite to the flux coming out of this surface. So if I separate these two, you know, this is like a mental experiment. I separate the two. I've got the same flux as I had originally. Because they're equal and opposite, they cancel. So the flux out of this half potato and the flux out of this half potato is precisely the original flux out of the total surface. Yeah? Now, it's obvious that if you got the hang of that once, I can do it again. For example, I might say, all right, I'll take this half, and I cut it again. And now, the flux out of this cut surface is equal and opposite to the flux out of this cut surface. So still, the total flux out of this piece and this piece is equal to the original flux out of the surface of this piece. Put the whole thing back together, and it's still equal to the total flux out of the potato. Yeah? So basically, I can keep cutting and subdividing again and again and again, and the argument must hold that the total flux out of the outer surface is the sum of the fluxes of all the little cut pieces inside. So now, Nigel Stone, I take a zillion cuts this way, a zillion cuts that way, and I make a zillion squared or something. Anyway, a very large number of tiny cubes. So all I've got to do is work out the flux from a single cube and then add them all up, because that will still give me the total flux out of the surface. And the view graph shuffling monster spared figure 0, and here it is. So you may, I'll just go through it very, very briefly. This is the computation of the flux out of any vector field C out of a small cube. Yeah. So basically, first of all, the flux out of face 1, well, because the surface, this is we're not infinitesimal yet. It's got a volume delta x times delta y times delta z. So that's the volume of the cube. Well, here we are on face 1, and there's face 1. The vector field here is C. Yeah. So it's x component is the flux is the value of the field C. It's the x component of the field C times the area. Obviously, I'm assuming that the field that the cube is so small that I can just take the value of C in the middle. And now, if I consider the flux out of face 2, you might think, oh, that's just going to cancel. It's equal and opposite. But the vector field will, in general, be a function of position. It's changing with respect to x. So the flux out of face 2, which is the value of Cx evaluated at face 2 times the area of this surface, we're considering that one and that one, but Cx2 is not quite the same as the value of the field at the first surface, because in general the x component will be varying with respect to x. I'm going in the x direction, and the field component Cx is slightly different in general at this face. And so the flux out of this field is the rate of change of Cx with respect to x times the distance I've moved. Of course, plus higher order terms, but we're going to take the limit of infinitesimals, so clearly we'll be neglecting them later, just like in our very first lecture last year where we did differentiation from first principles. So the flux out of face 2 is Cx plus dCx by dx delta x times the area of the face. So the flux out of those two faces added together, well, now this term cancels with this term, and we're just left. So this term here out of face 2 is this one is equal and opposite to this one, so they cancel, and all I'm left with is dCx by dx times delta x times delta y times delta z. Now, I think it's fairly obvious that I can apply the same arguments in the y and the z directions. At the moment, I've paired up the first two faces. So I've made that, let's say, the x direction. And there's a small flux through, net flux through this face and this face, if that's the x direction running across the lecture theatre. And that's the answer. I can likewise do it with this face and this face and this face and this face. And I will get, in that case, from the flux out of the cube, when I've paired the y1 with the y1, I get this. When I pair the z face with the z face, I get this. And so the flux out of this tiny cube has to be dcx by dx plus dcy by dy plus dcz by dz times delta x, delta y, delta z. Well, that's obviously the volume of the small cube. And instead of adding, and again we did this last year in the context of one-dimensional calculus, clearly if I've got the limit of the cube becoming infinitesimal, this, instead of summing all these little fluxes of these zillion bits that I've cut the potato into, I integrate over infinitesimal volumes. And because I get bored with writing this again and again, I give it an abbreviation. I call it del.c. And so if I integrate del.c over the volume, I have here, I've taken the step of going to the infinitesimal one. That's still equal to the flux through the outer surface. So it's equal to the surface integral of the normal component of the same vector field. And we're going to be using this again and again for important concepts like local charge conservation. We're going to be using it in our derivation of the speed of light calculation. So it's very important to get on top of that idea. So that is Gauss's theorem. I want to emphasize that this equation here contains no physics at all. That is pure maths. But because, and we've just proved it quickly, qualitatively, in 10 minutes, you'd have done that much more rigorously last term, it of course applies to the vector field E. E is a vector field. So being as this is mathematically true of any vector field, it is certainly true for the electric field E. Excuse me. Del dot E dV. So we've got that is true, and there is, I'll emphasize that. Let's make this equation 2,4. We've used 3 equations so far. Equation 2,4 contains no physics. It's pure maths. Absolutely no physics at all in that. That's true of any vector field. So now, though, wait a minute, we've got, and I'll rewrite it. So that's just true because it's true for any vector field. If it's true for any vector field, it's true for the electric field. But now we know from experience that Coulomb's law is true. You've learned how to rephrase Coulomb's law as Gauss's flux law of electrostatics. We know that the surface integral, this is now the physics. We know that the surface integral of the normal component of the electric field, the flux of the electric field through this surface, is equal to the volume integral of the charge density over epsilon naught integrated over the volume. Again, we called this equation 2,2. So if we've got those things that are both true, it necessarily follows, because the left-hand sides are identical, that the right-hand sides are identical. Now again, I'm going to write this in a 2-step calculation in this first lecture when we're getting into things. And in future calculations, I'll do it in 1 step. But clearly, the left-hand side of equation 2,2 is equal to the left-hand side, is indeed identical to the left-hand side of 2,4. So the right-hand sides would sure as hell better be equal as well. So we've therefore got that the divergence of the electric field integrated over any volume in space is equal to the volume integral of the charge density over epsilon naught integrated over the same volume. But now, this equation is true for any arbitrary volume in space. So the integrands, the things under the integral sign, have got to be equal. If you go back to our kind of, again, I won't keep burdening you with the sort of year 1 maths, but if the integral of f of x is always equal to the integral of g of x, then f of x is equal to g of x. You know, if you integrate them over any interval and they're always equal, then the integrands, dx, are also equal. So if you have the excuse me, there's a bit of chalk dust in the air already, sign of a new term starting. As these integrals are equal for any arbitrary volume V in space, the integrands must be equal, i.e. del dot E is equal to rho over epsilon naught. So this is to emphasize that we haven't discovered any new physics with this equation at all. But there are two extremely powerful reasons for reframing Coulomb's law in this way. The first is that Coulomb's law is only true when the charges aren't moving. Coulomb's law is not a general law. Coulomb's law is only true in this approximation. That's not a generally true equation of physics. That's only true when there's no dynamic magnetic field. So therefore, Coulomb's law is approximate, whereas, i.e. equation 2.1, the first Maxwell equation, let me just again emphasize equation 2.1 is true at every point in the universe, as far as we know. Now, this is quite a useful thing for a physicist to have, is an equation that's always true at every point in the universe. You could be inside a neutron star, you could be inside a nucleus, you could be inside a piece of chalk, anywhere. Always, at every point in the universe, the divergence of the electric field is equal to the charge density over epsilon naught at that point. So we've abstracted from Coulomb's law, we got to Gauss's flux law, and now Gauss's flux law is vice versa. Of course, I could go around the other way. I could integrate both of these over the volume, then replace that volume integral with the surface integral. That is called the integral form of the equation, and this is called the differential form. So we've got an equation that's true at every point in the universe. So this is a massive advance. There is another point which I will now develop, and that is that it's a more sophisticated way. I mean, roughly speaking, so we've got these three ways of expressing the same physics. This one is only true in static circumstances. This is generally true, and it's called an integral form, the integral form of Maxwell's first equation. And the differential form is more powerful because it's true at every point in the universe. It's not like integrating over some volume. This is true everywhere. And roughly speaking, you can say that it's sort of like that's the kind of larder, you know, that'll get you there. You want to get from, you know, York to London, you know, you can, you know, this one will do the job. You know, you sort of get up to about 35 miles an hour as you reach the M1. By the time you've got to Nottingham, you're doing about 45. You know, it'll get you to London, but it'll take you 7 hours or so. Yeah. This is kind of like, you know, the sort of Golf GTR, you know, a bit sportier. You can actually overtake the lorries, you know, with this one, and you can get there. This is much more powerful sort of way of getting. It'll still just, it's all electrostatics. All it will do is solve the same problem, like getting you from York to London. But now you're getting there in sort of, you know, 3.5 hours. This is the Aston Martin with the ejector seat. This is the really fast way to go to solve the problem. This is the really advanced, beautiful method. And this one, you kind of like, you know, the kind of, you know, the Golf GTI is doing 80, you go past them at 180 miles. Well, you know, I'm not advising you to drive at 180 miles an hour down the M1, but, you know, this one will do it. Of course, the problem is when you first start using this equation, if you've never driven an Aston Martin before, you'll probably stall. You won't get there at all, or you'll put it in reverse. Oh, blimey, I'm in Edinburgh. Well, you know, what happened there? You know, but or you might press the ejector seat button. You know, even worse might happen. But of course, it's worth going over to this way of doing it. And in particular, the reason for that is we're now going to combine that with another very important, if you like, revision of Kieran's course, and I want to relate. You see, again, one of the reasons that we do this first is precisely because the inverse square laws are what we're brought up with. So we start with electrostatics because you think, well, this is familiar. I know how to relate this apparently, very new-looking equation. That doesn't look like an inverse square law. You have to think about it to see that it corresponds to an inverse square law. And when you've got these simple types of fields, you can express them in terms of a potential. And that is precisely what is illustrated in figure, I think, 3 of the course handout. So let me just, we're now actually getting on, if you like, to the real sort of nitty-gritty into the course. And I shall talk amongst yourselves while the view graph shuffling monster is overcome, hopefully, at the front here. Ah, there they are. So, sorry, figure 2. The electric field E is related to the electric potential phi. And again, just to note that Kieran in his course used V, and V for voltage is a kind of obvious thing. But again, in this course, partly again because Feynman uses phi for electric potential, I'm going to use it. But also because I don't want to make any confusion. If I use V, well, at long range with a dirty blackboard, that might look a bit like the del operator. So, whereas phi doesn't look at all like the del operator. It was funny actually, I'm on this natural sciences board where there's a new degree starting next year, and physics is in most of the programs. One of the representatives from, well, shall we call it a lesser science? I shall leave it nameless. I don't want to get fired immediately. Said, do you know there's a lot of those upside down triangles in physics? What are they all about? Oh, well, anyway. Said, look, no, don't worry. It's all right. The electric field is minus del phi, or going the other way round. Phi at B minus phi at A is equal to the line integral of E dot S. Yeah. So these are, again, we discussed this, if you like, the equations 2, 5 and 2, 6. This is, again, probably the last time I'll mention the year 1 maths. We did this in one dimension. Of course, if you go one direction, if you differentiate phi, in the 1D analogy of this would be E of x is minus, again, straight back derivative, if it's a minus d phi by dx, and phi is equal to the integral of E dx. But of course, if we're in 3D, we have to perform the line integral, and this is precisely what is illustrated. And the point is, it's totally path independent. It doesn't matter how I go from A to B, and that's how I go from A to B is illustrated in figure 3. Yeah. I could go, you might think, oh, I could sneak around it. I could maybe gain a little bit of energy out of the field somehow by sort of going out that way, a bit radially, then a bit that way, then out that way, or I could go a bit that way, across and cross. It doesn't matter how I go from one to the other. This isn't path-independent integral, and so that's precisely why I can define a potential at this point. And likewise, if I was to do a complete line integral, if I was to close the loop and go from A to A, I must get 0. In other words, when I come back to the same point, I've got to be at the same potential. This is, again, emphatically not true for magnetic fields or dynamic electric fields. This is only true when Coulomb's law is true. It's true when all the charges are static. And because charges exert forces on each other, if you have two charges, they exert forces and they move. So it's a complete abstraction that is actually never true. It's useful as an approximation in many circumstances, however, and that's why we study it. So what I want to do now, just in the last couple of minutes, it's formal. This is developed slightly more in the VLE notes, is to say, we know that the electric field in this static circumstance can be expressed as a gradient of a potential. And again, I brought along something to illustrate the gradient operation as well, which is somewhere around, I hope. Again, if you find any trouble with the concept of a gradient, think about temperature and a heat flow vector. Temperature is a scalar field. If I had a little infinitesimal thermometer that I could put anywhere in here, I'd get a field where the temperature was a function of x, y, and z. Now, at every point I can define the field. Well, clearly, let's say over here it's hot and over here it's cold. Well, heat's going to flow, and it flows downhill. As temperature's going up, heat is flowing this way. That's why we have a minus sign. I would be able to say in this circumstance, the heat flow vector, well, there'll be some constant, but times the gradient of the temperature field. You know, with electric, E is minus del phi. There's no constant of proportionality. It is the gradient, whereas here we'd have a constant of proportionality. But it's the same idea, and again, that's developed on the VLE. So combining equations 2, 5, which is E is minus del phi, and 2, 1, first Maxwell equation, we have that the, excuse me, the divergence of del phi is minus rho over epsilon naught. Again, I've taken the minus sign across to this side. So I've replaced the electric field by minus del phi. But if I apply del dot del phi, that's the same as applying the scalar operator del squared. The Laplacian operator to phi is minus rho over epsilon naught. And that equation 2,7 is known as Poisson's equation. Now, in the end, of course, as I say, this is kind of like, you know, this is, you know, like you've added a twiddly bit. This is the Aston Martin with ejector seat, with, you know, amphibious sort of landing gear and so on. Poisson's equation will enable a professional physicist. I mean, that's a second-order partial differential equation, which you're studying this term. Obviously, the Schrödinger equation is a second-order partial differential equation. Second-order partial differential equations are of such massive importance in physics that if you want to be really good at it, you've got to get on top of them. However, this won't enable you to solve different problems to Coulomb's law. It's just a much cleverer, neater way of writing it. And like some lecturers could now spend absolutely weeks doing really complicated boundary value problems in electrostatics that you couldn't solve with any ease with Coulomb's law, but life's too short for that, and tomorrow we're going to let the charges start to move. Okay, yeah, see you then. No, sorry, not Friday, it's Friday in Blue 1, yeah.